Good afternoon, guys. So today we are going to talk about von Neumann architecture. You can see in the presentation slide von Neumann architecture. So before starting our presentation, I would like to introduce my team members. There is Michelle and Marushi. So let's move on to our slides. This is our content. So I am not going to introduce this whole part. The first thing is the introduction, and then we are going to talk about the von Neumann models. Like that, we are going to talk about until the advanced topics in von Neumann architecture. So before talking about this content, I would like to give you a single easy question. So anyone knows who is this? Any idea? Shah Rukh Khan. Okay. So why should I show this to you? Is there any relationship between this Shah Rukh Khan and this von Neumann architecture? Is there any relationship between? Yeah. No idea. Okay, actually there is no relationship between the Shah Rukh Khan and the von Neumann architecture. I just showed this picture to get your attention to my presentation. That's the only point. Okay, now let's move on to our next slide. Okay, who is this? Now you all know that is Shah Rukh Khan. So as a BA students, do you know who is this? The topic is also a von Neumann architecture. So any idea?
Von Neumann.
So he is John von Neumann. He is an American mathematician. Okay. So he is the founder of this von Neumann architecture in 1940. So let's move on to the history of this von Neumann architecture. So during the World War II time period, there is a project means Manhattan project. In the World War II period, there is a project which names Manhattan project. So anyone having an idea about this Manhattan project? Anyone heard this before? Like this word Manhattan project? No idea. So in this Manhattan project, the main purpose is to producing nuclear things like bombs. So it's a World War. So the main purpose of this Manhattan project is to producing nuclear things like bombs. So hope you understand what's going on. So what's the duty of this John von Neumann in that project? What's the duty of this John von Neumann in that project is he's having to make an electronic computer to make computations part. Okay, so that's the main role of his job role. So as a result of that only he produced this von Neumann architecture. That's the way this von Neumann architecture produced to the world. Okay, now let's move on to our next slide. Importance of von Neumann architecture in computer science. So this von Neumann architecture is the foundation of the general computer machines. That's the main foundation of the majority of general purpose machines nowadays. So these are the key points. This is a stored program concept, and there is the ability of programmability and the flexibility. So what is meant by this stored program concept? Did you heard this about before? Stored program concept. So we all know there are two parts in our data. One is data and the other part is instructions. So there are two parts. In the stored program concept, we can store these data and instructions in a once. In the same storage location, we can store these data and instructions in the same place. But before this von Neumann architecture introduced, we cannot do like that. We have to store data in one place and the instruction in another place. So this is one of the importance of von Neumann architecture. And the next part is programmability and flexibility. What is this programmability? Programmability is the ability of a system. Programmability is the ability of a system to program by to be instructions. We are having some instructions to using these instructions we are going to program. That's the main idea of this programmability. And next we are having sequential execution and universal computing machine. What's mean by universal computing machine? By using universal computing machine, we can calculate any of the logical part or algorithmic part. So anything we can calculate and store in that part using universal computing machine. That's the basic idea of this universal computing machine. And again, this von Neumann architecture influence on the computer architecture. So these are the key points of importance of von Neumann architecture. Now let's move on to our next slide. Now we are coming to a big interested part in this von Neumann architecture. So you can see here, this is a structure. This is the main structure with these described components of von Neumann architecture. So explain this part to you. I will use whiteboard a bit. So would you like to use this part or that part? That. Okay, so I will use that. Okay, now we are going to talk about components of von Neumann architecture. So before that, we should know what are the main components of von Neumann architecture. So let's write it down. The first part is input and output devices. In the von Neumann architecture, there are three main components. The first thing is input and output devices. So I write it down here. There are inputs and outputs. Okay, the first part is okay, there are input and output units, and the next part is memory unit. So the next component is memory unit. So in this structure we are dividing it into two parts. What are the two parts of memory units? We can divide it into primary and the secondary. So we can write it as this is primary. And the second part of this memory is secondary memory. Okay, so the second part is okay. So the last part is CPU. CPU is the last part of the components of this von Neumann architecture. So I will write it here. CPU. So we can divide this CPU into another three parts. Any idea? Main parts of the CPU. What? Adi. CU, ALU, registers. Okay. CU refers to what? CU refers to control unit. And there are registers. And we are having ALU. ALU means arithmetic and logic unit. So this is the main structure. It's the big difference between that, but I wrote this here because this will be easy to understand. Okay. So now I am going to explain you how the process is going down. So now we are having the main three components, input and outputs, and we are having the memory parts, and we are having the CPU. So this registers ALU, CU. As a combination, we are telling that's the CPU part. Okay. So think like this. Now we are putting an input like this 3 plus 2. We are using the keyboard and giving an input like 3 plus 2, and it's going to the primary memory. After going into the primary memory, it transfers this data to the registers, and it comes to ALU. The ALU unit is the unit which is doing this all logical things. So in ALU we can get the answer 5. So this is the addition 3 plus 2. We can get the sum as 5. So ALU calculates this answer and he sends back to the register, and it's come to the primary memory. So as we all know, we can't store data in like 1 month, 2 months. We can't store data in primary memory. So think like this. If you want to get the output now, okay, then we can get this data to our output device such as monitor or speakers. We can get the output, but we no need to get the output now. We have to save it then in our secondary memory, hard disk or pen drive or something. We can save this answer in the secondary memory. So if the days come, we want as output, again we can get that data from the secondary memory, primary memory, and we can get the output in the monitor or speaker, any output device, even a printer. Okay. So this is the main process running in the von Neumann architecture. Is there any issues in that part? Okay. Now we are going to talk about this central processing unit. So I stored here thought that there are three main parts. So these are the main three parts in central processing unit. And again we are having to talk about memory. So I told you there are two main parts. One is primary memory, it's we are calling RAM. It's a main memory, and there are memory, secondary memory. So the difference between this primary memory and secondary memory is the primary memory data can directly accessed by the CPU. That's the difference between the primary memory and secondary memory. But in the secondary memory, we are talking about secondary memory. The processor can't directly access data in the secondary memory. So if we want to get some data from the secondary memory, first that data wants to go to the primary memory, and after that only that data coming to the CPU. That's the difference between this primary memory and the secondary memory. And there are some examples for our input and output devices. So these are going to talk about future slides by Michelle. So this is the fetch, decode, execute cycle. So I will explain this part in my future slide because I think it's better. I will explain this whole part in my future slide. And the last part of this topic is instruction set architecture. That means ISA. Did you heard about this before? ISA, instructions data architecture. Anyone? Okay, no idea. Okay, now the basic of this is it's a group of commands. It's a group of commands which is inbuilt in the processor. Okay, in the manufacturing there is a group of commands which is inbuilt in the processor. So as this is a input inbuilt data, the processor can easily and directly access these data and decode and execute decode and execute part easily to this ISA data. That's the basic of this. So next we have to talk about this memory hierarchy. So for that I invite Michelle to continue this presentation.
Thank you, Shane. So I'm going to talk about memory hierarchy. Memory hierarchy refers to the organizations of different types of computer memories in hierarchical manner based on their speed, capacity, and cost. So the concept of the memory hierarchy is rooted in the principles of exploring the trade-off between these factors to optimize the overall system performances. The purpose of the memory hierarchy is to provide a storage system that balances speed, capacity, and cost. So, in other terms, hierarchy can refers as simply means as ranking. So, if we consider the access time, capacity, and cost, we can rank the memory units like this. So the levels are organized in such a way. The higher levels have less capacity, and they are faster, and they are more expensive. In the lower levels, they have larger capacity, and they are slower, and they also have they are less expensive. So, however, in terms cost and the usage of frequency usage, hierarchies triggers. If you move up in this, cost and frequency of usage increase. Memory organizations in Neumann architecture. The memory organization is a fundamental aspect that plays a crucial role in the functions of computer system. Here's the overview of the memory organization in Neumann architecture. So, memory organization can be divided into three parts: cache memory, and main memory, and secondary memory. So first of all, I'm going to talk about the cache memory. Cache memory is a small and high-speed memory located within the CPU. It's designed to provide fast access to the frequency used instruction and data. The primary purpose of the cache memory is to reduce the CPU access time to main memory, as accessing data from the cache is typically faster. So modern day systems have different levels of caches. So generally there are three types of caches mostly used in this today's system architecture: the L1, L2, and the L3 caching. So if you got an idea about the levels of these caches, L1 is the smallest, and used to store the frequency access data, which is second in priority. Finally, L3 caches are the largest of all these, and we also can call as a shared cache. So next I'm going to talk about main memory. It's also called as RAM. RAM is the primary memory compute system. It holds both instructions and data that the CPU actually use different program executions. Main memory provides larger capacity compared to the cache memory. And also it can be called as a volatile memory. Volatile means the contents are lost when the power is turned off. So overall memory serves a crucial bridge between the CPU and the secondary storage, providing fast and temporary storage for data instructions, which significantly impacts the performance for the computer system. So next I'm going to talk about secondary storage. Secondary storage also called as auxiliary storage or the external storage. Secondary storage is non-volatile storage media that the device used to store the data for a long time period or offline storage. So if we talk about the common types of the secondary storages, it includes hard disk drives, solid state drives, optical disks, and magnetic tapes and cloud storages. So next I'm going to hand over the presentation to Ashin.
Thank you, Michelle. So our next topic is to talk about CPU organization. So this is the structure we're going to learn. Is this bit complicated? When you see this, did you get any point? Okay, it's a bit complicated. So I will going to now teach this at a simple way. So before talking about this structure, I want to teach you what are these main components in this structure. So control unit is here. So I told you in there, but I didn't describe what's mean by this control unit. So control unit is the components which is doing the communication part. In the CPU unit, the control unit is the components which is doing and handling all the communication parts and is the control of this control unit. So that's the basic idea of this control unit. And the next part is arithmetic and logic unit. So in that, my example you see that arithmetic and logic unit is the unit which got the answer. So in this picture you can see this arithmetic and logic unit is performing to all mathematical calculations and logical comparison. So there are two parts. It is operand and opcode. So anyone knows this operand and opcode? What is operand and what is opcode? So I will explain this in our structure, CPU structure. I will explain this what is operand and what is the opcode and what is the difference between these opcodes and operands. Okay. So for this only you can think like we have that in that same example we get the sum of 3 and 2. So in the A as the integer operand we can get 3 and for B as the integer operand we can get 2. So opcode means what we want to do for this data. Now there are two data which is 3 and 2, but those are only data. Now I am asking what we going to do for this data. That's mean by this opcode. Now we want to get the sum of these data. So the opcode is get the addition like that. So as a y result we can get 5. So this is the process of this arithmetic and logic unit works. So now we can have to talk about registers. The register is a very small part in the CPU and we can divide these registers into two main parts. Those are general purpose registers and the special purpose registers, and after that again we can divide these general purpose registers into another two parts. Those are data registers and index registers. So after that these are the main parts of these registers. Now I am going to talk about some examples for these registers. So those are, you can see in the slides, PC. It's a one example for this register. PC means program counter. PC refers to program count, and again you can see MAR. MAR means memory addressing register, and MBR means memory buffering registers, and IR we can take it as CIR, that is current instruction register. So all of these parts I am going to discuss you in that structure. So hope you guys get a better knowledge what is the CU, what is ALU and what is register. Okay, now let's move on to our previous slide, which is this. Okay, for explain this part, again I would like to use the whiteboard. So I think it's better. Okay, now I am going to draw this chart in the whiteboard. The first you can see there is PC. PC is one of the example for registers. Okay, hope you will remember in that slide. PC is the one example for the resistor. So I am writing in here program counter. Okay, there is programming counter. The programming counter is doing the always counting the programs. That's why we are wrote there +1 mark. So this PC is always counting the programs. Okay, the next part is you can see memory addressing register. It's also an example for the register. So I write in here memory addressing register, that means MAR. After that we can see the memory part. Okay, in the memory, as we all know, there are data and instructions in the memory. Okay, there are data and instructions in the memory. Now, if we want to get some data or instructions from the memory, how we get that? We have to call that data. So, if we want to call that data, we need to identify which is the address of that data. So, it's like this as an example. Now, think. I want to call Lakshara. He is in L candy. So if I want to call Lakshara, I can only the way I can call Lakshara is I want to set his name. That's the only way. So like that, if you want to get any data from here, we need to call them by calling this address. Okay, that's the only way we can get the data from the memory. Okay, so this is MAR, memory addressing registers, and the next part is MBR. MBR is the part which is getting data from this memory. MBR is the unit which is getting data from this memory, and after that we can see there is CIR. In the CIR is doing the decoding part. Okay, in CIR refers to current instruction register. So in the CIR, he is doing the decoding part. Okay. So I forgot to tell you that now up to here process. You will remember that I skipped a slide which is fetch, decode, and execute cycle. So there are 3 parts in this. So this program counter and MAR and is going to the memory. And from memory, MBR getting the data from the memory. So up to here we are calling fetch. Up to here we are calling fetch, and after getting those data, MBR transfer those data to the CIR. CIR is the component which is doing decode. Okay. So now let's see what's mean by this decode. So say if I get the same example, 3 plus 2. Decoding means the CIR divided this into 2 parts. One is opcode and the other thing is operand. These are the 2 ways we can divide this instruction. Okay. So what's the opcode in here? I told you it's the instructions. What's the opcode in this example? We have to get the sum of 3 and 2. So what is the opcode? Not the operand. I'm asking the opcode. Plus. We have to get the sum. So, what are the data and operands? 3 and 2 are the operands. Okay. So, as the CIR is the unit which is divided these two opcode and operand. So, after this part, you can see from the CIR there is the ALU. ALU means arithmetic and logic unit. So after this part, CIR sending to these data to the ALU. These data is coming to the ALU because ALU the component which can get the answer for this. Okay, so in the ALU we calculate the answer as 5 and we transfer this to MBR. Okay, from MBR again we transfers this data. From MBR we again transfers this data to the memory. So this is the main process which is doing in the von Neumann architecture. So as I said before, if you want to get this answer now, we can transfer it to the output device. So otherwise we want to get the answer in some another day, we can save it in the secondary memory. So this is the basic of this structure. So is there any issues? Okay. Okay, now let's move on to our next slides. So I told this before, control unit, arithmetic and logic unit, registers. So nowadays the von Neumann architecture, some special features added to this von Neumann architecture. So there are DMA, NMU pipeline like that, multiprocessing cache memory. So these are some key points added to this von Neumann architecture after it's produced. So from these points we are going to talk about pipeline. The pipeline concept we are going to talk about now. So I will keep this like this. Okay, think like this. There is a car manufacturing company. There is a car manufacturing company. So this is their manufacturing building. This is their manufacturing company. This is the manufacturing company. So there are three main machines there. The one is to prepare the body. The one is to prepare the body, and the second machine is to fix the engine. The second machine is to fix the engine, and the third machine is to do the painting part. Okay, so these are three machines in the car manufacturing company. So now there are three structures of cars which are imported from another country. There are three car structures. I rename it as A, B, and C. Okay. So at first, A is coming to this manufacturing process. Okay, A is coming to here. So now A is in the body part. A is in the body part, and A is after completing this body part, he is going to the engine part. Okay, now when he leaves this body part and went to this engine part, you can see there is a space to B. You can see there is a space to B. But B can't come here without this von Neumann without pipeline concept is there. B can't come to here until A goes from out to here. The A should go out from this manufacturing process to come B to here. That's the theory of this. So now A is in the engine part. So after completing that, A is in the painting part. So after the painting part is over, A can execute this process. So after that only B can come to here. After A goes out, only the way the B can come here. But in the pipelining concept, we can write it like this. So first we are getting the A to the body part. First we are getting A to the body part. So after this assembling process ended, A is going to the engine part. Okay, now there is a free space in body part. So as there is a free space, the B can come to here. So now A is not in here, A went to here. So the engine part, and B, that's why the B can come to the body part. Okay, is it clear? Is it clear? Okay. So now A is in here. So after this process is ended, A can come to this painting part and B can come to this engine part. And there is another free space again in the body part, and then C can come to here. So this is how it's working in the manufacturing process with the pipelining concept. So you should remember that I told you a fetch, decode and execute. I told you previous slide what is this fetch, what is this decode, what is this execute part. So in the pipelining concept, without this pipelining concept, processor can't fetch, decode and execute more than one instructions at a while. Without this pipelining concept, processor can't fetch, decode and execute more than one instructions at a while. But with this pipelining concept, the processor can handle more than one instruction to do fetch, decode and execute more than one instruction at once. So that's the basic thing of this pipeline. So as the next slide we have to talk about this superscalar architecture. So in this, superscalar allows the processors to carry out several instructions simultaneously. So this is performed by implementing numerous separate functional units such as ALUs and CPUs. So this is a very basic part. So this is bit same with pipelining concept. So you can see there are difference between superscale and pipelining. So as this is not much interest time, not much important, I am not going to describe all these parts, but there is these points are in the slide. If you are interested, you can go through about these points. So next we are having to talk about input and output devices. So I invite Michelle to continue this presentation from here.
As you know, input and output devices are the essential components of the computer system that enable users to interact with the machine and receive information. So the program and data is read into the main memory from the input device of secondary storage and the controller of CPU input instructions. Output devices are used to output information from the computer. So as you all know, what are the examples for input and output devices? So I'm going to tell about that. And next I'm going to tell about the interrupts. Interrupt is a signal that's sent from the device or sent from the software to the operating system. So interrupts plays a crucial role in the input and output devices to facilitate efficient communications between the device and the rest of the computer system. So next I am going to talk about the direct memory access. Direct memory access is the method that allows an input-output device to send data related to the main memory and receive data directly from the main memory. So this is done to free up the CPU from the slow input and output operation activities and allow CPU to attend to perform other work while waiting for a relatively slow input-output data transfer to complete. So DMA control is the part of the motherboard chipset. Usually it's separated from the motherboard and it is not actually part in the CPU. So this is the basic DMA operation system. First we have the CPU and second we have DMA controller, disk controller and main memory. So as you can see, both four blocks are connected well together for help for the bus, and they are and let's also have an external drive. It's helped to become clear for a better understand. and they also have a buffer in the disk controller. Buffer is a really temporary storage unit. It's used to store data temporarily, and the reason for using the buffer is because the GMA cannot perform operations unless the data inside the buffer. So the communication between the CPU and the input-output devices. For an example, when instruction is a process request data from disk, data is first copied from the disk drive to its buffer. It's from the buffer that data is transferred to the main memory. Disk control settings facilitate the process. So finally, I'm going to talk about the issues with traditional input-output data transfers. First, slow transfer speed, limit bandwidth, third, security risks. Fourth, lack of real-time updates, with incomplete and data loss. Sixth, lack of collaboration and accessibility. So next I'm going to hand over the presentation to Margie.
Thank you. Now I am going to present about assembly programming language. First let's see what is the assembly language. Programming, we can divide programming language to two parts, such like low-level programming language and high-level programming language. What do you think about assembly language is high-level or low-level? Yeah, that's it. Correct. Assembly is a low-level programming language and it close relationship with machine code. And assembly is human readable programming language and it provides direct control over hardware and it uses mnemonic instruction for operation and manipulates data through registers. And assembly codes is stored in plain text file. Usually we use ASM file extension to save assembly code test files, but it is not compulsory as in Python. We use .py likewise, and after we code in assembly code, computer cannot understand what is the assembly language. First first running before it's run, assembly code is should convert to machine code. It is done by assembly. So this slide there has the assembly language code and the assembly language machine code. First, assembler is converted source program to object program, but program one by one. Assembler convert of source program to source program machine code one by one. Here has a small assembly code for getting sum of two numbers, but first introduce variable is store the result of sum of two numbers. After start program, first input move the value in A register and second move the value in B register. After add the values together, then add the value in B register then value in A register. After store the result in move the result A register to the memory location. After we finally can get output from this code. And in this part, let's see what are the advantages and challenges in assembly language. First, advantages in assembly language are high optimacy and efficiency, ideal for performance critical tasks, and use device drivers and end system. What are the challenges in assembly language? Challenges in assembly language are requires deep understanding of computer architecture and manual management of low-level details, and debugging and maintenance can be complex. And this is let's see how programming the Neumann architecture using assembly language. Here, this part can be this part in 4 steps. First is understand the architecture. Second is write assembly code, and third is assemble code, and fourth one is load and execute. First, we see what is understand the architecture. First, we write the assembly code. We should understand what is and we should learn what is the memory organization, and we should learn CPU structure such like its components, register, LU, and control units. After understanding about architecture, we can write assembly code by using Neumann instructions and multiple register of calculation. After access Neumann for data storage. After writing assembly code, as I said previous, we cannot run assembly code like white, and we should convert assembly code to machine code. So we use assembler to it, and after convert to machine code, it's transferred to memory and can start the execution from initial activities. And let's see what are the benefits and challenges and example of von Neumann programming. Benefits are efficient code execution and fine-grained hardware controls and performance optimization. Challenges are deep understanding and manual memory and register management and debugging complexity. Example of von Neumann programming are creating algorithm for arithmetic operations and implement control flow with condition and loops, and accessing memory for data manipulation. This is the debugging techniques in assembly language. First is print statement and breakpoints and debuggers and logging. And other is optimization techniques. Here, first algorithmic optimization called proofing and compiler optimization, memory management, and proofing tools and performance analysis